Okay, so today we're going to talk about some advanced rational functions, and we're going to talk about the types of discontinuities that they have. So, a graph is going to be discontinuous if you cannot trace the graph without picking up your pencil. So if you think about looking at this graph right here, if I try to trace it, I'm good here. I don't have to pick up my pencil till I get right here where x equals -2. And x equals -2, this is going to go down, 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 down forever. To get to this piece of the graph, I've got to pick up my pencil to graph the next piece. So this graph, we would say it's discontinuous at x equals -2. And this particular type of discontinuity, we've used this word a lot already, but it's going to be called a vertical asymptote. The y goes to infinity or negative infinity as x approaches a given value. So in this case, our x right here is -2. So as our x values get closer and closer and closer to that dotted line, our y values are either going to go to negative infinity when we approach it from the left side, or if we approach it from the right side, it goes to positive infinity. So that's what our vertical asymptote is going to look like here. So we would say here that we have a vertical asymptote at x equals -2. Now, I don't always have a graph there. So sometimes I might ask you this question when all you have is the equation. How could we tell just from the equation that we would have a vertical asymptote at x equals -2? Very good. So if I plugged in -2 right here, it would give me a 0 in the denominator. And that would mean I'd have 1 over 0. And 1 over 0 is undefined. Alright? And so if my denominator equals 0, then I have to have a discontinuity somewhere in my graph. So if I just had this equation, I could say x plus 2 equals 0, and I could just subtract that 2, and x would equal -2. There's my vertical asymptote there. So, we kind of already talked about this. What causes a vertical asymptote? A 0 in the denominator that is not canceled out. Okay? We'll talk about that canceling here in just a minute. So, you'll see a lot of these where you don't have graphs. You just have equations, and they ask you for vertical asymptotes. So whenever that happens, if it's one like number 1, you're just going to take your denominator and set it equal to 0. And in this case, we'll subtract 7, so x will equal -7. There we go. So this would be our vertical asymptote here. Okay, questions on the first one? All right, now you're essentially doing the same thing with the second one. You're taking that denominator, you're setting it equal to 0. But to solve that, it's got a square, so you can't just simply move the 2 over like we did on the last one. What would we have to do to solve that? We would factor. We also could do quadratic formula or completing the square, but factoring is generally what we're going to be using for these. Most everything will factor. So we would have x and x. We need to get a +2. But have a -3 here, so what should I use? What? 2 and 1. And both of them should be negative there. That'll give us a -3. So then make sure whenever you do this, that's set equal to 0. So you got to remember to do this step where you set each one equal to 0. Now, I don't care if you write that down or not. You can do this part in your head. But your answer has to be x equals positive 2 and x equals 1. So this would be our vertical asymptotes here. Now, let's talk about this canceling out, because that is going to cause something that's going to look a little bit different. So here, we had potential for something to cancel out, but it did not. So let's look at one where it does. So next thing we're going to talk about is a point discontinuity. A point discontinuity has several different names that you might see it called. Okay, point discontinuity is also called a hole, because it's where there's going to be a hole in the graph, but the pieces of the graph match up. It is also sometimes called a removable discontinuity. So if you see any of those three phrases, a point discontinuity, a hole, or a removable discontinuity, we're talking about the same thing there. I'm probably mostly going to call it a hole in the graph. But remember that that point discontinuity and that removable discontinuity also refer to the hole. So let's talk about the graph of x plus 5 over x plus 5. Now if I have x plus 5 over x plus 5, most of the time, that is just going to give me 1, right? If I plug in any number, it's basically going to give me 1. So, like if I pick numbers to plug in, like if I plug in 2, I would get 2 plus 5, which is 7, over 2 plus 5, which is 7. 7 over 7 will give me 1. So I have the point 2, 1 here. If I plug in a number like 4, this time I would get 4 plus 5, which is 9, over 4 plus 5, which is 9, and it's also going to give me 1. Got the 0.41. I could plug in 0. 0 plus 5 over 0 plus 5 would be 5 over 5, which would just give me 1. All right, so this is getting a little bit boring. It seems like it's always going to be 1, except what number is not going to give us 1? Negative 5. Okay, so at negative 5, if I plug in negative 5, I would get negative 5 plus 5 over negative 5 plus 5, which equals 0 over 0. 0 over 0 does not equal 1. 0 over 0 is actually what we call the indeterminate form, but we could also just call it is also undefined there. So right here at negative 5, what happens is I get a hole in the graph. If I'm graphing it by hand, I'm going to show that by using an open circle. So what really happens is this graph should just be a horizontal line everywhere except for at that one single point where it has to be undefined because your denominator equals 0. Right? All the way up to negative 5. So at negative 5.00001 or at negative 4.99999, it still equals 1. But if you ever get to exactly at the point negative 5, it's undefined. Okay? This is called a point discontinuity or removable discontinuity because it could be fixed with one tiny point, right? If we had just one point that we filled in right here, then it would no longer be discontinuous. So just one point could remove that discontinuity. That's why you see those phrases there. So let's look at the types of problems you're going to see about this. Okay, a hole is caused by a 0 in the denominator that does cancel out. So let's look at what this looks like. So I'm always worried about the denominator. The denominator is where I'm going to have discontinuities. All right. So for every problem, we're going to factor the denominator and the numerator, although in this case, the numerator does not factor. So our denominator, we're going to factor it. So I'll have an x here and an x here. I got a negative 15. I need to get a positive 2 in the middle. What numbers should I use? Plus 5, negative 3. That'll work because 5 times negative 3 gives me negative 15. 5 minus 3 is going to give me that positive 2. So what happens here, it must be factored first before you can do any canceling. But this x minus 3 and this x minus 3 right here can cancel out. Now, to talk about this discontinuities, for my discontinuities, are going to happen wherever my denominator equals 0 before I cancel anything out. So that would be at x equals negative 5 and at x equals 3. I have discontinuities here because these two things in the denominator equal 0. So like if I have x plus 5 equals 0, that means x equals negative 5. And then if I have x minus 3 equals 0, then x would equal 3. Right? So I definitely have discontinuities there. It doesn't matter if they cancel or not. You have a discontinuity. The canceling determines what type of discontinuity you're going to have. So if they cancel, you have a hole. So at x equals 3, we'll just have a hole in the graph. Whereas for x equals negative 5, that is a vertical asymptote. It's really important to remember that discontinuities always come from the denominator. So we're always worried about that denominator, not the numerator. The numerator, the only thing we care about it for is to see if anything cancels or not. Let's see, I need to think about the schedule. How much time for that? Go back 15 minutes. Okay, I think we're all right. Okay. Okay, so if we look at example 4, I want to factor top and bottom, although the bottom is what I care the most about. So if I factor the numerator, I'd have x and x. I got a plus 9, a minus 6 in the middle. I'm going to need a minus 3 and a minus 3. There. In the bottom, how do I factor x squared minus 9? X plus 3, x minus 3. That middle term is missing. You might remember the fancy name for it. What do we call it when we've got x squared minus 9 or x squared minus 25 or something like that? This is called a difference of squares. I'm not going to ask you that. It's just a good term to know because you might hear teachers say it a lot. So, remember, we're always looking at the denominator for our discontinuities. So, they are going to happen at x equals negative 3 and x equals positive 3. What I'm doing there is just taking the opposite sign. All right, you get your x equals negative 3 from this first one, x equals positive 3 from that second one because you're setting that denominator equal to 0. Alright, so my x minus 3's can cancel. Right here I've got x minus 3 and x plus 3. They cannot cancel. Alright, so for my x minus 3, the point that goes with that is the x equals 3. So this one is going to be a hole in the graph, or removable discontinuity. The x equals negative 3, that's going to be a vertical asymptote. Please do not do this. Some students want to do this. They want to start crossing stuff out inside of those parentheses. You cannot do that. Okay, it's just got to be the entire factor that cancels out. Okay, all right. So we're just still doing the same thing. Discontinuities. So we only look at the denominator. This one won't factor. So we only care about the denominator. So it's going to be, we're going to set that denominator equal to 0. And so x equals 5, if we move that 5 over. All right. What type of discontinuity are we going to have here, Hallie? It's going to be a vertical asymptote because it does not cancel with anything in the numerator. Okay, for example 6, we've got x plus 4 over 2x squared minus 7x minus 4. A little bit tougher factoring in that denominator. Remember, when you got a number in front of your x squared, you're going to have to put that 2x here and the x here. And you got to do some guessing and checking. So you need something that will give you a negative 4. So you're either going to have to use negative 2 and 2 or negative 4 and 1. In this case, I think it's going to work if we put the minus 4 right here and the plus 1 here, right? Remember, with those, to check, you just check your inner terms. You get positive 1x. And your outer terms, you get negative 8x, which will give you negative 7x, which is what you want. So looking at that denominator, I have to set it equal to 0. So I can see really easily that this x minus 4 is going to be x equals 4. Some students get a little tripped up whenever you have 2x plus 1 and they'll say it's x equals negative 1. That's not correct. Remember, we're doing 2x plus 1 equals 0. So you got to move that 1 over. You'll get 2x equals negative 1. And then you'll divide by that 2. So x is going to equal negative 1/2. So these are our discontinuities here. Does anything cancel? It does not, because up here we've got an x plus 4 instead of an x minus 4. So both of these are going to be vertical asymptotes. Notice I didn't do anything with the top. There's no x equals negative 4 because it's from the numerator. You can have zeros in the numerator. That's fine. Okay, so let's talk about functions being continuous or discontinuous. So if a function is not discontinuous, it is continuous. Right? So if you have no discontinuities, then the function is going to be continuous. So another way that you're going to see questions asked is they're going to ask if the function is continuous on the given interval. So right now, what we're looking at are going to be rational functions. So there are some other things that can cause discontinuities, but right now we're thinking about that denominator. F of x equals 3x minus 7. Are you ever going to have an x in the 0 in the denominator there? No, because you don't have a denominator, right? So this would be continuous everywhere on the interval they've asked us to look at. So from so continuous on the entire interval there. So from -2 to 3. Or if you want to use this, you could do -2, 3 if you prefer that interval notation that we were using. All right, for 8, we are going to have a discontinuity here. Maddox, where's that discontinuity going to be? Or I should say, we're going to have one somewhere on this graph. It may or may not be within that range. So, good. It would be at x equals -9. Does -9 fall in our range from 0 to 9? It does not. So, this would be continuous on 0 less than x less than 9. So, it's continuous everywhere there. Okay, now, here, if I've got 3x plus 2 over 3x plus 2, those would cancel out. But remember, even if they cancel, it still causes a hole in the graph, which is still a discontinuity. So I'm going to take that denominator and set it equal to 0. So that'll be 3x equals -2 when I move the 2 over to the other side. I'll divide by 3. And so x will equal -2/3. Okay? I need to go back and look at my notes because everything's ended up being continuous here. I need an example that's not, right? So this is also continuous on 0 to 1. Not everywhere, but on 0 to 1. I would have this as continuous because our discontinuity is not in that range. Now, up here, I didn't ask because the question doesn't ask, but up here this would be a vertical asymptote because that does not cancel. But right here, we would have a hole in the graph. It doesn't matter, though, what type of discontinuity. Even if it's just a hole, it's still a discontinuity. So if they're asking for if it's continuous, it doesn't matter there. All right, let's see if we can get these last couple done. So I'm going to try to move pretty quickly. The top, we're going to factor. We'll get 2x and x. We need, somebody get it for me, minus 4 here, plus 3 here, I think will work. Because that'll give us a 3x and a -8, which will give us -5. So that's how that one factors. Then we would have x plus 4, x minus 4 in the bottom. I'm moving a little quickly on that factor, and it might take you a minute to get it. But so we're looking at the denominator. We got x cannot equal, let's see, x equals -4 and x equals +4, right? Right here is our -4. Right here is our +4 because we got to set those equal to 0. The x minus 4 will cancel, so we've got a hole here. And the x plus 4 does not, so we got a vertical asymptote. It really doesn't matter, though, whether or not it's a hole or vertical asymptote when they've asked you where this is continuous. So the graph is going to be continuous everywhere except for those 2 points. So we would say this is continuous on, I'm going to use interval notation, so it'd be -infinity up to -4. -4 to 4, and 4 to infinity. Notice I use parentheses with all of those because we're not including -4 and we're not including 4. Alright, and this last one we're going to do real quick. X to the fourth minus 81. This is a difference of squares, but I've got x to the fourth, so it's going to have to be x squared minus 9, x squared plus 9. And my denominator will factor into x plus 3, x plus 1, I believe. Now, it looks like nothing cancels at this point, but is there anything I could factor further in the numerator? I could do that x squared minus 9. I could do x plus 3 and x minus 3. Now, the x squared plus 9, I can't split it up because it's a difference of squares. You have to have a minus sign for it to break apart. So it would look like this. My denominator is x plus 3, x plus 1. And so those x plus 3's are going to cancel. So I'll get x equals negative 3 and x equals negative 1. Now, it doesn't ask this, but just for extra practice, this is a hole in the graph right here. This is a vertical asymptote right here. So I'm going to be continuous everywhere except for those 2 points. So I would say it's continuous on negative infinity to negative 3, negative 3 to negative 1, and negative 1 to infinity. Okay. Questions?